So let's look at the electromagnetic spectrum. So notice the rainbow in the cover slide, and in a rainbow you'll always find red at the top when you have a single rainbow. Remember, your rainbow colors are Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, with violet having the shortest wavelength and red having the longest wavelength. So, electromagnetic waves are formed when an electric field couples with a magnetic field, and they're perpendicular to each other. Fireworks we see due to the light that's emitted, and what forms this light? It's an electromagnetic wave, and it's a vibrating electric charge, which you can think of as an electron. You might remember from your chemistry class that the electrons, when they gain energy, they jump one or more energy levels, and when they fall back down, they emit a photon. In the case of fireworks, we see a photon of visible light. So light. Sometimes it behaves like a particle, and sometimes it behaves like a wave. We call it wave-particle duality. You might recognize these diagrams as the electron orbitals that you studied in chemistry, SPDFs. As I've mentioned a few times, it's great to study science because then you get the comics. So Albert Michelson is a scientist who was born in Prussia and then lived in, of all places, Virginia City during the Silver Rush, and he also lived in San Francisco. He approached President Grant when he wanted to go to the Naval Academy and he had not received an appointment from his senator nor congressman. And President Grant gave him a presidential appointment to the Academy. I want you to remember Albert Michelson because he, as well as a man named Morley, last name Morley, measured the speed of light. But they are also famous, or Albert's famous, for discovering that ether did not exist. At the time, in the late 1800s, they thought light had to travel through a substance, and they called this substance ether. And Michelson and Morley set up an experiment where they sent coherent light, which means all the waves are in phase, so all the crests are lined up, all the troughs are lined up. And they believed that if there was ether, when they sent this light through this semi-silvered mirror, this is like your rearview mirrors where it kind of dims, you get some light through and some light is reflected. And here some of the light's reflected and then comes through to the other, then comes through to the detector. And here the light comes through and then goes through the detector. Because the light is traveling perpendicular to, as well as parallel to the ether, they felt the ether was surrounding this, they thought they would see the light somewhat out of phase, and they didn't. So they got a negative result, and it really proved they did not have ether. To measure, here's just another depiction of it. In position 1, our reflected light goes directly to the detector at A. Here's our rotating mirror. The reflected light goes to the distant mirror, and here we have the reflected light going to B. Now, one way he measured the speed of light is that he took an octagonal mirror that was rotating, and he had light come through, just a beam of light, hit a concave mirror, and that light hit the rotating mirror, and he was able to detect it at point T. Since he knew the distance, 35 kilometers, as well between the rotating mirror and the plane mirror, and he knew the rate of rotation, he was able to calculate the speed of light. At the Naval Academy in Annapolis, there's a a monument to Michelson. I hope to visit one day. Now the speed of light, we're going to use 3 times 10 to the 8th meters per second, or 3 times 10 to the 5th kilometers per second. Remember, we use the variable c for celer, which means fast in Latin. So the speed of light is c whenever we use an electromagnetic wave in a vacuum. So our wave equation, c equals lambda times f, frequency. So the speed of light equals wavelength times frequency. So wavelength, remember, is just crest to crest, trough to trough. Anytime you can measure a complete crest and a complete trough. Frequency is how many wavelengths pass you per second. So when we're talking light, our cycles are wavelengths. And remember, our units are hertz, or per second. So parts of the electromagnetic spectrum. Remember, it's radio, microwaves, infrared, visible light, ultraviolet light, X-rays, and gamma rays. So I do want you to remember that radio waves have the longest wavelength, gamma rays have the shortest wavelength, radio waves have the smallest frequency, gamma rays have the largest frequency, and they all travel at the speed of light. So wavelength and frequency are inversely proportional. So one way to remember those is to remember a saying for them. I like run that, in victory you excel greatly, with the first letter in each of those words representing the electromagnetic spectrum section. All of these waves are emitted by the sun, and some are blocked. So radio waves, a little bit about them. They're the longest wavelength. They vary from about 3 kilometers to 30 centimeters in length, from 100 kilohertz to 100 gigahertz. And you can have AM, FM, you also know it as TV. Remember, AM are kilohertz, and FM are always megahertz. Cell phones can also use radio waves. Cordless phones also use radio waves, and you can find that information if you look at your device. So microwaves, this is a Doppler radar installation, and microwaves are from 30 centimeters to 3 millimeters, from 300 megahertz to 300 gigahertz. We use them in microwave ovens. Remember, microwave ovens work because they resonate the water molecules. We also have cell phones. Remember cell phones had radio waves? So microwaves are right next to it. So they're about the same. Doppler radar also used microwaves. Infrared. Your remote control uses infrared. Those waves are about 3 micrometers, 3 times 10 to the negative 6. They vary from gigahertz to terahertz. Tera is times 10 to the 12. We know it as heat. And we have remote controls that use it. And someone said something the other day that caught me, was infrared sauna. And I was like, isn't that redundant? Now visible light is Roy G. Biv. It goes from 700 to 400 nanometers. and it's about 750 to 400 terahertz. And there's a nice visual depiction of it. Ultraviolet. Ultraviolet's in the nanometer range, less than 400. And you can see it goes from 10 to the 14th to 10 to the 16th hertz. It causes sunburn. It also causes cataracts, so you do want to wear your sunglasses. We have telescopes up in space that detect UV radiation from extraterrestrial objects. X-rays are the next ones down, less than 10 nanometers, times 10 to the 16 hertz. And gamma rays are our smallest, less than 1 picometer, but up to 10 to the 20th hertz. So I do want you to remember the electromagnetic spectrum, and you don't have to memorize how long the wavelengths are, but you should be able to know that they travel at the speed of light in a vacuum. And we'll practice using C equals lambda times F some more in class.